Okay, let's get started. I'm very happy to introduce Victoria Stodden from Columbia University. Victoria is spending this semester here in Berkeley, which is also teaching our master's capstone course. So Victoria has a PhD in statistics and a law degree from Stanford. Her main research focus is on the very important problem of reproducibility in science, and she's going to talk about that today.
Thank you. Thank you for the introduction and for the opportunity to address everybody here today. It's actually really an honor. This is a brand new talk that I get to debut on you, and there are some new results that actually have not been yet presented in here. So hopefully we get a lot of time for discussion and feedback. So reproducibility in science, reliability in statistical and data-driven research. So what I'm going to do is try and motivate to you, first of all, why this is an important problem that we need to think about and care about. It arises from issues in big data and big computation, so I'll try and trace how these changes are changing how we think about what it means to produce good inference and reliable conclusions from data. I'll talk a little bit about my thesis. My thesis was a couple of years ago now, but what I'd like to do is tie this in and I'll bring it back in future directions. I'm going to spend some time also thinking about sources of error when we have statistical issues, computational issues, and empirical issues all leading towards how we can think about and start to understand this issue of reproducibility and what it might mean when we're doing statistical research. I've spent some time doing empirical work modeling policy responses around reproducibility, so part of thinking about solutions to these issues, so I'll talk to you about some of this. I want to present to you also frameworks for thinking about software as a method and why this is something that actually I'd like to submit to you could be thought of as something properly within a statistical framework. And then, as I mentioned, I'll talk about future directions. Okay, so when I say reproducibility, the first thing you might think of is something like, yeah, that sounds pretty good, but what's the big deal? You know, why is this suddenly on our agenda? What I did is I started thinking about how computation is impacting the type of research we do as statisticians and also as data scientists. And I went and I looked at the June issue of the Journal of the American Statistical Association, and I went back to 1996. I was interested in a couple of issues. So one is, are we even doing more computational work as statisticians, or are we sort of in a steady state in terms of the type of scholarship that we're producing? So even in 1996, you can see about half of the articles in that issue of JASA were computational, and it only took until 2009 for pretty much everything to be, at least have a computational element. Even if it wasn't primarily a computational paper, they had an example or simulation or something in there.
Is this theory and methods or applications?
Theory and methods, yeah. And then I looked to see whether there was code with any of this. So this was really what I was interested in, like whether we were communicating that aspect of the research or not. And so back to 1996, nobody really mentioned anything. This is a pretty low bar. So if you sort of gave me any hint of where I could sort of get code. And this increases, and then we get up to about 20%, and I probably should do another one in 2013 from last June. But so this is so much better. Infinitely better than zero, but still we're looking at about 4 out of 5 of these computational papers where we're not able to really dig in and see the implementation of the results that are being presented to us. Some results Ian Eades published in 2011, he looked at 500 papers. Now this is primarily in the life sciences, so a different group, and found about 9% had their full primary raw data deposited. And in a result I'm going to motivate for you a little later in the talk, I'm estimating with my co-author that we can replicate 27% of the papers that are being published in Science today that have a computational element to them. Okay, so the framing that I've been thinking about regarding reproducibility is really down to how does this fit into the scientific method. So we all know that traditionally there's 2 branches to the scientific method, deductive and inductive. So thinking about the deductive branch, mathematics, formal logic, all this deductive reasoning. And in the empirical branch or inductive branch, you can think of things like statistical analysis of controlled experiments. And I'm sure everybody here has heard all this hype over the last 5 years, maybe 10 years, about all these new branches of the scientific method. We've got a 3rd branch of the scientific method, large-scale simulations, a 4th branch, data-driven discovery, and it just seems all sort of very exciting. So I just sort of looked around quickly on the web, and there's a NIST workshop in 1995. So in 1995, they're saying it's common now to consider computation as a third branch of science besides theory and experiment. And then this is a book from 2009 that was sponsored by Microsoft Research. This book is about a new fourth paradigm for science based on data-intensive computing. So those are sure very grand words. A lot of this is coming, of course, from the impact of technology. So there's three big shifts. I won't go into much detail here because I think everyone in the audience is very familiar with at least two of these. Big data, data deluge, high dimensional data. We have new paradigms for discovery, new methods that are coming out of analyzing these new types of data. We're also being pushed in terms of just high performance computing. We have resources that are allowing us to ask questions and seek answers in new ways. So that's a little bit what is underlying all this discussion of third and fourth branches. Something I don't hear people talking about, but I think is an equally important change, is now we have intellectual contributions to science, bona fide intellectual contributions, really only captured in the software. And I think probably everyone in this room can imagine that that's the case. So as an example, here's Lior Pachter. This is from November of 2013. You can even watch the video on YouTube. Very early on in the video, he talks about his software being part of supplemental materials for publications that he's just put out and how unsatisfying that was because it wasn't reviewed. And he's saying that the software in the supplemental materials contains ideas that enable biology. So we've really got all this stuff now for the first time in the software. Okay, so why do we have these branches of the scientific method, and why is it so important? It's because we're trying to get things right, and we all make mistakes. There's mistakes possible in all aspects of the process of doing research. It's just error-prone. So the deductive and empirical branch, they've had hundreds of years to think about what it means to make a scientific contribution in one of these branches, and they have very strict standards or established standards for what it means to make that contribution. So in mathematics, of course, you don't publish a mathematical finding without including a proof, right? In the empirical branch, there's an entire machinery of hypothesis testing, appropriate statistical methods, a very clear, structured way that you communicate these methods in your paper. There's an entire protocol about how you do this. Both of these are about transparency, verification, and really trying to root out error. So my claim, computation, both of these changes, big computation and big data, they present only a potential third or fourth branch to the scientific method until we develop comparable standards around computational research similar to the first and second branch. Now, it's not a damning criticism. We've had about 20 years to think about this, and there's been hundreds of years on the other one. So the theme of the talk is how do we go about thinking about what these standards might be? And what I'd like to present to you that I think that this is something that statisticians are uniquely placed to think about how to raise these standards so that the computation and the data-driven analysis are really contributing reliable, real scientific knowledge. Okay, probably many of you have seen discussions about reproducibility in the press. I just grabbed some for you, like LA Times, telling us that science has lost its way, and these are all from within about the last 6 to 8 months. Economist had a big issue on how science goes wrong, and really a lot of this was around reproducibility and reporting. And then, perhaps more interestingly, Science and Nature are both coming out with articles that address their own perception of their lack of reproducibility in what they're publishing. So here in Science, this is from January of 2014, the editor-in-chief says, the article, I'm sure you can't read this, but it says reproducibility, and she's putting in new standards for reporting, particularly statistical standards on how to communicate research in science. Here, Nature, April of 2013, announcement, reducing your reproducibility, we must try harder, and so on. So where is this coming from, and what does it all mean, and what does that have to do with statistics? Okay, so I started thinking about how to parse this term reproducibility. I think there's at least 3 different components and different places where, for reproducible research, this can break and you can end up with irreproducible research. The first one is what I'm calling empirical reproducibility. This is what nature is largely science is largely addressing here with their standards. The way I'm thinking about this is somehow our traditional standards in the second branch are broken. We're not reporting things. There's been a gap. There's tacit knowledge or something. But fundamentally, it's not due to the technology. It's somehow over these hundreds of years, the standards have either degraded or should be taken a second look at. I think of computational reproducibility as the reproducibility that comes from these new technological tools like the computation and big data. So what do we need to do in terms of standards for computational research, and how do we understand how to draw reliable inferences from big data or big computation? The third one where we can break reproducibility is in poor statistics, as I'm sure I don't need to tell people here. And poor statistics doesn't necessarily mean obviously poor. It can mean things like over-reliance on p-values that an entire field does, for example, that can break reproducibility. Okay, so I've parsed this a little further, so I don't think you can actually read all this text, but I'll put the slides on my website in case you get motivated. You can go back and read it. But there's different ways, different levels you can think of what you might think of as a reproducible result. So the first one, reviewable. So is there enough in the discussion of the finding where you can independently assess these results and judge them credible? So you could sort of think of something as reviewable. A little more sophisticated, maybe something is replicable. So there are tools available that would allow you to duplicate the results of the research. So you can just sort of run through with code and data and reproduce, replicate the actual results in the paper. Confirmable, the main conclusions of the research can be attained independently without using the software provided by the author. So you can go ahead and do some independent research and actually confirm those findings. So a slightly different way of reproducing the results. Is it auditable? So are there sufficient records such as data and software being archived so the research can be defended later if it's necessary? This doesn't necessarily need to be public. So you could be doing your work in a lab, and at some point, if there's controversy, you could actually say, yeah, it's perfectly auditable. I've got all the provenance and code and so on here. The final one is reproducible, where we take this auditable research and we actually just make it openly available so that other people can reproduce the result. So the way that we describe this is well-documented, fully open code, data publicly available, so you can audit the computational procedure, replicate, independently reproduce the results of the research, and extend the results or apply the methods in new situations. Okay, so that's a lot to keep in mind as we go through. Most of what I'm going to focus on in my research and in this talk is the last one, where we have code and data made openly available so that other research can go ahead and verify your findings and also extend it and apply it.
Can I ask you a question?
Yeah, of course.
I'm a little lost therefore on what the difference between replicability and reproducibility is, because it seems like at the core of both is that the code and the data are there and some.
Yeah, that's true. That's true. So this is so reproducibility has a little bit more in the terms of it's easier to go ahead and take it and apply it in new places. So that's kind of a little bit of a higher bar rather than just sort of replicating the sort of hitting return in a sense. Yeah.
Maybe I've misread what you wrote, but I thought the distinction is there enough description that someone could code it up for him or herself and try it, versus are you actually producing the artifact that produced?
Yeah, it's a nice distinction. So here with replicable, there are some tools made available, but not to the same level here. So for example, you could have black box code here, for example, it's still replicable in some sense. But I will flesh these out as we go through the talk as well, so we'll see the differences. I did want to put this, it's becoming a well-known quote now, actually, as these issues have gathered more steam. There's a professor at Stanford, John Claerbout, who started, I think, the earliest example is 1993, really reproducible research. He wouldn't sign a student's thesis unless he could, in effect, on his system, hit return and regenerate the thesis. This bled over into how I was trained as a PhD student, and this is a quote from 1998 with David Donahoe as my advisor. The idea is an article about computational science in a scientific publication is not the scholarship itself, it's merely advertising of the scholarship. So in the case of computational findings, the argument is that the actual scholarship is a complete set of instructions and data that generated the figures or tables or your results. So that's kind of been something of a framing philosophy. So this is very obviously going back to like 2005. So this was part of my dissertation. And with that philosophy in mind, one of the things I did was pull together, we had 13 papers with 11 authors, and we pulled them together around this theme of sparse modeling. This was 2005, so this is sort of the beginning of trying to study these ideas, and everything was reproducible. So we had code here. It was MATLAB code, which people were critical of us for, but it was there, and data were there, and they were housed in a structured format within MATLAB that would allow you to go and replicate. I think you can still do this. It's still there. So if you really want to replicate the work, I think you can do that. Okay, so also in my thesis, one of the things that I was focusing on that actually went into that sparse lab package was how do you deal with this very high dimensional data where you have many more variables than you have observations. And what we did in the thesis, just to be brief, because I'd like to come back to it with future directions, is we took this notion of sparsity, and if you're comfortable making this assumption that your vector of estimated coefficients is actually sparse, so you have a true underlying sparse model, then what we could do is actually recover this model. So what we wanted to do is estimate for some k that's less than the number of observations that we have, come up with some linear model y equals x beta plus some noise. So the question was, how do we select k? So what we did is I leaned on some work of my advisors who found an interesting result. So the first thing we did is we developed this phase diagram to present the results. So on these axes here, we have how underdetermined the problem actually is. So this is n over p here. And on this axis, we have k over n. So how sparse is our true underlying model. And then we were able to set up a series of simulations. And what this blue line is telling you is that we had some theory telling us that we think that we'll be able to recover a true underlying model here, and then have this model kind of break at this phase transition point here. So the theory says, what we would really like to do is look for our L0 norm that recovers this underlying model here. This is in the noiseless case. And then we have theory that says actually what we can do is actually solve this convex problem, the L1 norm, here, and actually for free solve the L0 norm problem under very broad conditions. So for my thesis, what I was doing was I developed these suites of problems each with sparse solutions. So we had some level of sparsity in the underlying problem and some number of variables, some number of observations and some number of variables. And so what we did is then we just evaluated how close we could actually get through mean squared error. So were we recovering this true underlying model? And we would expect something like a phase transition. So we did this for quite a few algorithms, and I just chose two up here. So we did this for forward stepwise, which you just see this model being recovered here at very low levels of sparsity. So if your true underlying model is quite sparse, forward stepwise is doing okay, and then it sort of falls off this cliff very dramatically with any kind of complexity underlying in your true model. And then we made a small adjustment. We just said, okay, so for including terms in the model, instead of doing it according to forward stepwise, essentially greedily adding terms by size of the t-statistic, if we did this with the false discovery rate thresholding, maybe we could be more sensitive. And here you see this is the exact line we saw with the phase transition from the previous slide, and you see this recovery. And so it exactly breaks down where you would expect. And I don't have time to go into it here, but we saw exactly the same thing for things like Lasso and Lars and other types of model selection algorithms. Okay, so I'll come back to those later on, because what I'd like to do is use those as a basis for pushing on this reproducibility issue. So I'd also like to convince you that reproducibility is a statistics issue, and it's something that statisticians have an ability to uniquely contribute thinking to. So if you think about all these statistical issues like false discovery, p-hacking, people running lots of models and then sort of choosing the one that comes up with a significant p-value, overusing p-values as a threshold or misusing them, all the multiple testing problems, file drawer problems, and people not recording or adjusting p-values appropriately when they do their work. This is, in my experience with applied work, this is unbelievably common, and there seems to be, in a sense, some lack of awareness of how this can affect the interpretation of results. You can see even things like, I've seen in some journals, sensitivity analysis where they run a whole lot more models and just try and show you that theirs actually is really good. And then this all comes to also poor reporting and tracking practices. Like, do we even know what's happened and how to interpret these statistical findings? Okay, things like data preparation, how you've treated outliers, they tend not to get reported as well. And the science certainly isn't settled on how we do this. These are largely statistical questions and empirical questions. And just even things like how have they done the sampling, or how have they applied methods? And I mentioned earlier on how Science magazine has brought statisticians into its editorial review board to try and check on these. They're worried about even just, not just a field that misapplies methods, but just people who are unaware of a lot of issues in statistics. And a little more subtly, so how robust is the model to parameter changes or perturbations in data? I'll come back to this because you can also think of reproducibility issues if you think about replicating the entire experiment as, in a sense, a data perturbation question. Okay, and then there's all these things. Investigator bias to previous findings, conflicts of interest, and so on, that may even subtly and unconsciously lead us to different results or non-replicable results. So one of the things that I was interested in is how journals are actually reacting to this. And so here are the new policies that Science enacted in 2014. So they want to make sure if you're publishing in Science, you've got what they call a data handling plan. So they're trying to get an idea on what have you done with outliers, or how have you pre-processed the data. They want to know your sample size estimation for effect size. They want to know whether samples are treated randomly and whether the experimenter is blind to the conduct of the experiment. So, and then as I mentioned, they're putting statisticians on their board of reviewing editors. So this just happened, and there's certainly concerns around, and as you know, the article is called Reproducibility, concerns about what I've been calling statistical reproducibility. Okay, so in order to understand how, for example, journals could impact reporting and also reproducibility in the literature, I chose 3 ISI classifications and carried out an empirical experiment. So I chose statistics and probability, mathematical and computational biology, and multidisciplinary sciences. The idea being I'm trying to get journals into the sample that actually publish computational work. I ended up with 170 journals, and then we created this data set that had all sorts of descriptive information about journals and so on, like impact factor and citations. And then we went and looked at what their policies were in June of 2011 and June of 2012. So I'll show you a couple of snippets from that work. There's an entire paper that goes with it that has more information. But the very quick answer is that journal policies could roughly be classified as required as a condition of publication. Exceptions would be things like privacy issues or other issues that it's actually illegal to share the data. Required, but we'll pretty much publish your paper anyway. It's not something that we pay that much attention to. And then language that encourages it or has some kind of implication, and then of course they just don't mention the issue at all. And the numbers at a glance look low, but to me this actually looks much higher than what I would have expected. And you see this shift here from about 67% who are ignoring the issue of data sharing down to about 62% in a year. And to me this means that, surprisingly, that journals are actually picking up on this issue and taking steps in this direction. I was also interested in the same questions for code. And code is a far lag behind journals, and it's going in the same direction, but you can see also that it just doesn't receive the same type of attention that data receives. There seems to be a lot more understanding of open data than there is around open code, but there's progress in all of these, particularly in encouraging of code sharing. Okay, with this study, we did a fair amount more work, but we came to understand that the journals that were comfortable making new requirements on their authors were the very high impact ones. It's not surprising that Science is coming out with subsequent changes. Lower impact journals are much more hesitant to make demands on their authors. We see this type of rapid adoption, and even though right now this isn't something that's anywhere near ubiquitous in publishing standards. Supplemental materials and data policy, they tended to go hand in hand, and I didn't see any statistically significant relationship between open data and code and open access policies, like whether or not you can actually just immediately access the article. And these data supplemental materials policies seem to sort of lead code. So I think there's opportunities for richer modeling of how these policies are adopted here. I also surveyed members of the NIPS community, the machine learning community, and I was asking them, because this is all NIPS folks up until 2008, and I was asking them about their latest NIPS paper and did they share the code or did they share the data? The idea being, okay, so there's a set of sort of levers from journals that we can empirically get a handle on, and there's also the researcher's point of view in terms of what works for them or what doesn't work for them in terms of understanding sharing. So I actually had 1,008 NIPS registrants. I restricted it to basically American institutions, research institutions and schools here, because they're all under, to some degree, the same legal structure. And I ended up sending the final survey to 638. So I had a 23% response rate. So here's what they said. So for the folks who did share code and data, by and large, the reasons they were doing this were not, personal gain. You can see a little bit in there, but mostly it was things like encouraging scientific advancement, sharing in others, and so on, being a good community member, improve the caliber of the research. Getting others to work on the problem, you're sort of thinking, well, maybe there's some self-interest there, increasing publicity, very likely self-interest, wanting feedback and finding collaborators. So this is why people were trying to make their work better known through code and data sharing. They didn't talk about things like for reproducibility purposes, for example. For the folks who didn't share, all the issues that they came up with were, by far the biggest one was it just takes a lot of time. Yeah, Ben.
So what was the form of the survey? Did you give them questions or they're pre-writing what they thought?
It's a great question. I had a web form, so they just had to click on a link to go there, and then I had radio buttons. So some of this, I did a fair amount of research to try and choose these categories. So we had hypotheses from the literature that we actually set up for them, and then after all of them, there was a big text box. So if I missed anything, they could just throw it in there. And it looks like we kind of got most of what the actual incentives that people were facing. Anything else? Okay. So basically the first one, it takes a lot of time to document and clean up code and data. Incentives aren't really aligned. I know quite a few outstanding researchers who don't really like writing research papers, but they somehow get that done. So this is something where it's just, at this point, not rewarded. And other people said, I don't want to be an IT service. I put code out there. I don't want to receive a lot of emails that it doesn't work when I install it. It's going to get stolen. So how do I get credit for the work if I share code and data? This surprised me, how high patents and legal barriers were on people's minds as a problem with not sharing code and data. Some folks told me, I don't want to share my software. I want to build a company around it. Things like this. I don't want to go through administrative hoops. I might actually get scooped. I don't want to advantage people that I'm actually competing against, and I just don't even know where to put this stuff. You can see that when they don't share, it's a lot more about my own personal, like, I'm going to get hurt if I do it. Okay, so thinking about in software, where do these statistical issues arise? So resolving issues in reproducibility in computational science, encoding good statistical practices in how we actually carry out the computational work itself, I think, is a key part of the solution. And I've been doing some work thinking about how software can interact with actually doing better statistics, not just from straightforward applications like p-hacking and the file drawer problem, where if we had sort of better management of the statistical experiment as it was going through, but also how do we actually track and code and communicate what was actually done in the experiment. Okay, so we can permit verification and comparison and extend all these same statistical notions of integrity to statistical software practices. So there's been an enormous amount of work, and I don't think I need to tell anyone in here, about how to think clearly and quantitatively about an experiment when you want to draw inference from it. So you think about things like, how is your sampling done? Do you really have a random sampling? What's your experimental design? These are all issues that no one would bat an eye that they're concretely and squarely statistical issues. I think we can extend this too to how do you support this with statistical software. So what notions of responsible creation of software objects or data objects that allow people to draw reliable inferences and communicate these reliable inferences to other people. So I think this is really a new issue in foundational statistical research. Okay, so I took this image from a talk by James Berger, and I wanted to also mention experimental bias. So this is a little bit hard for you to see, but I'll explain what's going on. So particle physicists were estimating constants in their field, and what they would do is they would publish their estimate, and they would have error bars, and then someone would improve the experiment and they would publish the new estimate with error bars and so on. And so what these plots are for different constants over time, and you can see the error bar around the estimate, and what actually happens is they converge on the true value. So the point of the plot is to say that for some reason, we seem to be highly influenced by the previous publications when we publish our results. So you don't see anyone kind of jumping to the right answer. It's all this kind of gradual chipping away and moving the entire literature there step by step. And so you see these sort of hidden biases creep in. Okay. So in December of 2012, I co-organized with a number of other organizers here a workshop and as part of the ISERM series at Brown University, and it's called, this is a very small font that I put here, Reproducibility in Computational and Experimental Mathematics. Much of what we were trying to do here was bring many different researchers together to talk about these issues, how it interacts with mathematical research, how it interacts with statistical research, it meaning computation, and then how do we think clearly and quantitatively about how to do effective inference and reliable inference from this type of work. Okay, so from this workshop, what we did is we came up with this workshop report, which was fairly lengthy. The workshop was a week long, and we had about 100 people, and actually Philip was there as well. And what we did is we distilled this into a report, and we've published pieces of it that basically point to it. This is fairly lengthy. I think it's about 20 pages in Notices of the AMS and also in SciAm News, arguing that we need to flip thinking about this on its head. And right now, a lot of the way computational science is done is maybe as an afterthought, I might share code and data, and that might be good for the reasons we saw, say, in the NIP survey. Maybe it will amplify your work, or maybe, you know, people will be able to build on it. But really, what we're arguing here is that we need to flip this the other way around and have this type of computational, empirical, statistical research done in such a way that it's naturally open, so that if it's closed, that's the exception to the way it really is. So we have a lot of, okay, don't read this, I'll explain it to you, but we have a lot of recommendations about how to think about communicating effective experiments in computational science. Okay, so one of the things that we thought about were standards for publication. So this is very different to what I just described, how science has moved towards some more stringent statistical standards. These are things like, were your assertions precisely stated in the paper? Do you state what your computational approach is? And is this an actual test of your hypotheses? Do you cite your software and every algorithm you employ? There's a really big problem in incentives that comes from we just tend to use software, we tend to use data, and there isn't really standards for citation. So are the citations intact? Did you talk about your hardware platform? For many problems, they're largely platform agnostic, but for some, there's very specialized hardware, and you need to understand settings, or it relies on the hardware and interacts with it in some way. Do you have the details of data reduction and all the analysis methods that you included in there? Parameters, for example. A full statement of the results. Did you have the code available? And this also includes input and output data. Function calls, computational instructions, alternate avenues of research that you may have explored that didn't actually end up as a discovery, but you still explored them. Perhaps you did some statistical tests when you were doing this. And then, of course, the citation issue. Okay, so those were some of the things that came out of the iSerm workshop. So this is my new work that hasn't yet been presented, so I'll give you the warning. Okay. So this also continues on the empirical work about journal policies. So the next question is, so maybe all these journals have these policies that are moving towards code and data requirements, but are any of them actually effective when it comes down to like the brass tacks of reproducibility? So I noticed that Science Magazine had changed its publication guidelines in February of 2011, and it says, all data, so I put the red in there, obviously, all data necessary to understand, assess, and extend the conclusions of the manuscript must be made available to any reader of science. Okay, so data has to be out there, and you should be able to get it for anything published in Science after February 11, 2011. All computer codes involved in the creation or analysis of data must also be available to any reader of Science, so you should be able to get the code too. After publication, all reasonable requests for data and materials must be fulfilled. Any restrictions need to be disclosed in advance. Okay, so the idea was, well, let's see how well that works. Yeah?
So is the journal planning to have the staff to do this? Or are they pushing the effort on
They're pushing the entire effort out to the people.
Because, you know, back compatibility 10 years later?
Yep, yep. So that's, yeah, that's a really important issue. So I actually talked to an editor of Science, and I said, well, what happens if you make the request and no one answers? And they just said, well, you know, reproducibility has always happened in the community. It's always happened post-publication, and it's going to continue that way. So that's sort of our problem. But if they don't answer, if you report back to us, we'll retract the paper, is what I was told. So I set about testing this. So I wanted to know two things. Did anyone answer? If you ask them for code or data, I mean, we probably all have a prior expectation on what you would get. And then if you got stuff from these authors, was it useful? Were you able to even replicate the result? Like, what types of materials were you actually getting? Was this something that bolstered your confidence in those findings? So we took a sample. Well, we actually went through from February 11 to June 29th, so a little over a year. We skinned out all the we needed to have computational articles, like real findings. So then we took a random sample of 204 of these articles, and we said, can we get the code and data from them? So is their policy effective? Can we reproduce the results if we got the code and data? And then would these ISERM standards, the ones that I just sort of dragged you through that, the whole huge list and the unreadable table, but would those standards have been effective in remedying any failures that we saw when we did this? Okay. Okay, shoot, I should have had, well, anyway, okay, I'll go on with this. Okay, so here's what actually happened when I emailed. So of this random sample, we went through the random sample, and 24 of them actually put code and data with the publication. We had no need to email them. So everything was just provided. Then for the other 180, we sent an email. We went through IRB at Columbia, and everything got approved, and we finally sent the email. No response, email bounced, so that was 49 out of 180. And I got things like, well, it's impossible for me to share code or data. I refuse to share it. You need to talk to someone else. I emailed corresponding authors, so people should have been responsive. They wanted to know why. Okay, that's great that you're emailing me, but what is all this about, and why would you want my code or data? They just seem to not really have this. I didn't say, by the way, it's in the guidelines. I just emailed to ask them. And actually, we did this. I had an undergrad working, and we set up the mail program to email from the undergrad. So, there was no, it was sort of like, there's no sort of name recognition involved in any of this. Yep, I'll follow up with you next week. I'm really busy right now. And then many people sent us back to supplemental materials and said, look in there. Which it wasn't, because we went through all of this stuff before we did it. And then 65 of them actually said, sure, here you go. And because of IRB, I can't show you some of the stuff we got in this 65, but some of it was really beautiful. Like, they were sort of well-organized pages with tutorials on how to use their software and how to access the data and how to generate the results. Okay, so we came up with about a 51% compliance rate when you take the 65 and the 24, and I gave these impossible to share people a break in there. Okay, so then we did the hard part of the ones where we had code and data. We parsed them, and we tried to actually go ahead and replicate and see what we could do. So 56 of the 89 articles were potentially reproducible. Just upon inspection, it looked like we had a shot at it. And then we chose a random sample of 22 from this 56, and then we tried for that 22, just because it's actually hard and intensive to do the replication. So 56 was a big challenge. We took it down to 22. So you'll be happy to know, after all these papers went through all these hoops, we got 19 that were replicable, the tools allowed and so on. And then we actually got to 21 that we could reproduce. Now, I was working with a postdoc on this. She's a very talented programmer. She had to do some work. So there was some scripting there. She would maybe have to install or update libraries, and we thought that was okay. So we did the extra work to do the reproducibility. So we got nearly all of them for the 22. Primarily what happened is the authors would send us code that had changed since publication, and we didn't know what the previous version was, and so that would break reproducibility. Okay, all right, so this is the previous plot, and I axed off all the writing just to show you of the 20, okay, so here we had 56 papers that had code and data, and how did they comply on these lofty and expansive criteria that came out of the ISERM workshop. And things like, did they describe their result? They all did this. Things like what their computational approach was, we had 82. Did they cite the software? Up to 80, which was good. Discussing the hardware was pretty miserable, 13%. Arguably, some of them may not have needed to, but this is just not something that's on people's radar. Discussing statistical analysis, 91, so not everybody was fully clear there. Parameters used, like, did they discuss them? Did they tell us what the parameters were? They discussed them. This must be both 85 here. Okay, told us the results. Made the code available, 77%, gave us function calls, 40. Okay, so some of these things that were broken in the work that we tried to replicate could have been filled in here with more information and more version control actually on their code. Okay, we also looked at verification and validation, so issues, concepts that come out of scientific computing, and we were interested in whether the code actually solves the problem that the authors think it's solving. So that's verifiability, and we had 34 out of 56 not solving the correct problem, and I'm happy to kind of go into this a little more in questions. Is that did they come up with even the right mathematical problem at all for what they're trying to address? And are you able to check that these results agree with other experiments or observations? And that's 51 out of 56, so that's a validatable. So this starts to, it starts to bring in these issues of, are they actually asking the right question, and are they taking the right methods as an approach to the question? Okay, our very early preliminary conclusions on this. 49% did not, either through non-replying or asking, more sort of pushing back on us. We never got their code and data. We actually gave them 2 weeks and a follow-up email in 2 weeks, and we didn't get it. And then we forgave the 2 that said they couldn't. So we replicated 19 of the 22, and for reproducibility, we were able to push this up when we did this for 21, chosen from our 56 potentially reproducible articles. So now our estimate is that probably if we did all 56, we'd end up being able to get the results for 48. And just to break down what actually happened in our random sample, we had model details missing, code missing, and code changes since publication. Those are the problems that we ran into. So a lot of it in software, not in data. And a lot of it in methods and how the software ties into the statistical analysis. Not so much, I just couldn't get your data set, which is a problem people have been working on longer than code. Okay, unreadable, but we're estimating 27% of the computational articles published in Science since February 11th, 2011 will actually replicate computationally. Okay, we're getting a little bit low on time, so I'll go quickly through this. One project I've been working on is really a pilot platform of how to link together code and data with a published article so that prima facie work can be reproduced, but also as a place to learn where these gaps are and understand how researchers actually are finding barriers to sharing, or whether they can actually create reproducible research and what's standing in the way and what's enabling. So we also here, it's called Research Compendia, and so if we have code and data, we'll actually run and provide a certification for papers that we can reproduce, for example. Okay. So what we'd like to do in the future with this is use this as a platform, since we're receiving data, receiving code, to do larger scale validation of findings, and be able to actually understand this stability of results and have sensitivity checks on much bigger data sets than an individual researcher might have access to. I'll just go quickly through this. It's in GitHub if you're interested. Okay, so future directions I've been thinking about. So computational reproducibility, it's really addressing, and so for example, Research Compendia and the work I was doing in Science addresses whether these fixed codes, like these snapshots of codes and data, can actually replicate results that were published at a fixed point in time. What it doesn't do, so this allows you to, you can validate, verify these results. You can reconcile differences in independent efforts. If you go ahead and recode results on the data set or slightly different data, and you want to understand how the methods are different, open code can allow you to actually reconcile those differences. But it doesn't tell us whether these findings are any good, right? Whether they improve our understanding of the world. So what I'd like to do is push on this a little further. This is the next stage, I think, in my research. So we would expect that for findings like this, these independent repeated replications would come out similarly, right? So possible sources of variation, you may see perturbations in the underlying data, which would therefore cause changes in your final estimated value. So you would naturally expect perturbations in independent repeated samples, repeated draws of the data. And so the idea is in real-world applications, like for example, in the science articles that we looked at or articles in research compendia, what happens when we do these perturbations in the data? How much do our results vary? So in other words, how tolerant should we be of divergences in independent replications? Like how can we understand a notion of sort of confidence intervals in that way? Same with perturbations in methods. So how we change analysis or just the stability of particular analysis methods themselves. Of course, we all know that small changes some methods are very robust to, and some will change your outcome quite a bit. Okay, and so this I think, because we're tracing errors through, allows us to build a relationship with literature in validation, verification, and it should be uncertainty quantification there. Okay, so what I'd like to do is take these problem sets that I used in my thesis and then really quantify the impact of the data and model perturbations in a very controlled way with simulations, and then we can assess what it means in an independent sense to do a replication. So we could maybe have guidelines to understanding when something is lending supporting evidence or when it's far enough away from a value that it's actually counter evidence. Okay, and I'd like to really push this out onto examples too after doing the simulations. Okay, so uncertainty quantification, we can actually extend these notions, including these data and model errors and software encoding issues. So I think pushing this especially in high dimensional data would be very interesting and very fruitful. So I think I'm out of time and I'll leave it there for questions. Thank you. Yes, Julie.
I ran into an interesting problem along this. I gave a talk a few years ago to some social science graduate students, and I told them that replication was so important, to just really for this latter purpose, to see what holds up.
Yeah.
And that I said in medicine, people replicate. You read about replication, but you don't read about it in social science. They told me that their advisors discouraged them from doing replication studies because they weren't original and they didn't get any credit for it.
Yeah, well, that's true. Yeah.
It was really discouraging. How do you fight that?
Yeah, so this is a huge problem, actually. So I hear anecdotally postdocs in some fields, like in geophysics, for example, they actually will replicate before they start a new project. They'll take the existing literature and get the results and build on it. But in the social sciences, I don't think it's common at all. My undergrad was in econ, and I know that world. And that is a huge problem. So if I was to, if I didn't have this in a larger study, any one of these replicated science articles, I can't imagine submitting that for publication by itself. It just wouldn't be considered original, or and so on. So, so something I'm hoping maybe with research compendia is, I didn't get a chance to go into it in detail, but there's one compendium page for each paper with coding data available there, and it links back to the original paper. So I could imagine a second compendium page for, say, an independent replication like this, and then that's maybe lower status than a full journal publication, but you can still get it out there, and those pages can be linked, and you can see that other people have been replicating that work. So I think that's actually a structure of the literature problem, because if people are doing this work, it's useful and it can get out there. Yeah. Yeah.
What are your thoughts on the temporal durability of software changes?
That's a great question. Yeah. Yeah. So I don't have all the answers to that question. So what I would like to say is that's something that that we need to work on. So we need to work on when you release software. I think having it running for 5 years is probably a reasonable goal that we could think about. And also, what dependencies do you have? What other pieces of software does it run on? So Research Compendia runs software, and we have different versions installed for when people submitted the stuff. So we're actually working on solutions in Research Compendia of very lightweight virtual machines that can actually do this replication, and you don't need actually the entire sort of machine packaged up, but just what you need to do the replication to try and preserve it. But that's an open question, and that's a tough one. Yeah, but I still think that having the code available, even if you can't run it, it's still useful. You can still get in there and see if they're magic numbers or what their parameters were. Yeah, Philip.
So the same kind of question. It's not just the particular instructions that you typed it's the entire environment in which
Yes,
your software
yes,
is running.
yeah.
It's the version of the operating system,
Yes.
it's the version of R, it's the version of
Yep.
whatever, and it operates differently on different platforms.
Right.
And on some level, all of that matters, but if you want to take all of those things into account, the most natural way to do it is to encapsulate it in a virtual machine or something, in which case you have a black box. You don't really get to look into the guts and understand what's going on. So how do you
Well,
surf that
it
line?
depends on what type of virtual machine you're using. So I would really like. I don't think it's that useful to have the black box, especially if the code is fairly short scripts. They can just be shipped alongside, and you can have that inspection. But I think you get into very interesting questions when you say, okay, but a black box in software is actually much more general than just a virtual machine around some scripts. You could imagine some of the scientific computing codes that are hundreds of thousands of lines long. They're code bases people have been working on for decades. I'm not going to read them. They can be open source all they like. I mean, maybe I can trace. It would still be good. Like I can trace in maybe a few pieces and sort of maybe debug something that's not working well. But we really need to think about testing and how do we actually query a black box and understand its behavior. That's, I think, the only way to tractably deal with this. And it's the same issue. As soon as our software isn't working, if we end up with this black box, then at least we can sort of understand some of the behavior.
So to what extent do you think test-driven design or packaging tests with the software?
Oh, yeah.
Is
Yeah, so I should have talked about that more. So that's something that in open source software, which is not scientific software development, and they have different goals and they do different things, but some things they are more advanced on than scientists is how they share and collaborate on software. So you wouldn't think of submitting your software contribution to an open source software collaboration without tests. So saying, here are my benchmarks, here's what I've done to show that this works and why I think it's right, and then this all goes in. Right now, it's a very new idea across computational sciences within the academy. So this is something where I think testing in a sense is almost trivial. You could almost think of your original data as the first test that you could ship with this. And then you could have like more trivial tests in there too, like throw in a matrix of zeros or whatever is appropriate in the case. And you would just have those there so you knew that your software was behaving well. Yeah. Yes?
So, just relates to like policy and science. So like even like development, because of both p-hacking and replication,
Yeah.
The journals won't really enforce the policy, they'll just do exactly science does. So we've got like the grant-making agencies enforce it. So Hewitt, Gates, USAID, they will want like both pre-analysis plans to prevent p-hacking.
That's great. Yeah.
And they will also then fund the software repository, right? So the offshore to the researcher, right? So the question is, why isn't like NIH
Doing that?
Yeah, NIH.
Yeah. So I can speculate. Maybe that's the next empirical. No, I think so. NIH. I don't actually know the relative sizes of the community. My guess would be this is a smaller community around one journal, and so there's less diversity. And NIH is running the gamut on all sorts of, and it's just got that monolithic inability to. And I've seen the same thing in my work with NSF as well. That it's just very difficult for these big structures to kind of, even though everybody kind of knows they need to go in this direction. But there's also, as soon as you vary, you go even within a discipline, within a subfield, problems are different enough that what it means to do reproducible work can shift. So I can't just sort of make a mandate, thou shalt put data out there and code out there. It's like Philip's point, the code needs to be very structured for that problem so it's actually effective and makes reproducible research. And then what data means can be for many researchers, that's the starting point. They collect the data and then they start their analysis. For others, they'll do the software and the simulation and get data as an output. So even the language and the terms are very different. And I'm just assuming that problem's more amplified for NIH. In NIH's defense, they are extremely advanced in setting up data sets and having open data requirements much more than NSF. So I think they're moving in that direction. They just haven't really brought code into their thinking, in my opinion, at this. Although they're starting to. There are some software plans that are required now for some solicitations.
More questions? Okay, thank you.
Okay, thank you.